Welcome everybody to part 4 of our NavMesh VR tutorial. Looks like today might be the last one in this little mini series, although I do plan to do some follow-up videos as I perfect some of the techniques that we've used so far. But it looks like that at the end of this video we'll have a completely working a little NavMesh demo in VR. Before we get started, however, I want to make two small changes to our project. The first is on the camera itself. I'm going to change the IOD to 6 centimeters instead of 6.5 centimeters. I've asked a few people to try out the little demo that I made once everything was working. And I found that most people said that with a 6 centimeter IOD, the experience was more comfortable, especially after having my kids have a try with it, who were obviously much more than us adults, and 6 centimeters seem to be working quite nicely as a good middle ground. I also found out after some research that the PSVR has got a setting near 6, and I think some of the other platforms, I think including Daydream, use it as a default as well. Although don't hold that to me. I might have mixed something up there or gotten something wrong, but it seems that 6 is a better starting value for your IOD. The other change is a fix, which we need to do in our main NavMesh script, and that has to do with our looking at function that we added over here. It turns out that the looking at function doesn't change the transform itself. It actually returns a new transform. So while this nicely calculated what it was supposed to be calculated, it then discarded the results. So we simply need to copy the result into itself, and it will actually use the correct transform. Now, the reason why I didn't catch that was that our default camera location was close enough to what it was supposed to be doing, so it didn't stand out. But once I started doing the navigation, which we'll be doing in this video, I suddenly realized that it wasn't actually working. Alright, so in this video, the first thing that we want to do is create a method for the user to move around our little world. It's fun to play this game from a fixed camera, but especially when you want the little robot to move around and go on top of things, it does help to have several points from which to view the world. But it's not as simple as the original NavMesh application was, where obviously you could use the mouse and drag the screen around to rotate the camera around the center point. In VR, we have a limit as far as the interaction is concerned with the user, and one of the ways that that's very often solved is by using what the user is looking at as a means to perform certain actions. I've added a little sphere, just a small little mesh as a placeholder to allow our navigation to work. And what we're going to do is we are going to place a number of spheres around our world, and when the user looks at one of the spheres for more than a second, we will teleport the user to that location of that sphere, and in that way allow the user to move around our little world. Now, instead of just putting that sphere in our world a couple of times and duplicating all the code that we need to use for that, we are going to create a scene that we are going to use multiple times and put some of the logic into that scene that will help us move the player around. So let's start there and start with creating a new scene. There we go. As always, we need a root node in this scene, and in this case we are going to use not solid, static body. Now, static body is one of the physics entities in Godot that the physics engine can use. The static one is one that stays in place. We have a rigid body, which things like gravity can work on. We have a kinetic body for player logic. I can't out of the top of my head remember what the fourth one is. But we're using the static body here because we want our sphere to be fixed in place. And the reason why we are using the physics engine for this, and not just put the sphere in the scene directly, is that we want to use raycasting to see or find out whether the user is looking directly at our little sphere. And Godot nicely does that for us with these physics bodies, with these physics entities, because you can completely automate that. We'll get to that in a minute, but yeah, that's why we are starting with our static body, and I'm going to rename that to be a nav point. Now we need to add two things to our nav point. The first is a mesh instance, and that's simply going to be our mesh. So we're going to load our sphere here. There we go. We have got a nice little sphere in there. And we need to have a collision shape. And I suddenly realize I shouldn't name that one shape. I need to use the other one. So that's our mesh. This is our shape. Now, the shape and the rigid body or the static body, they work hand in hand. So the static body is the physics entity that receives all our events and that the physics engine uses, while the shape, the collision shape, is the entity that allows Godot to know the physical presence of this body in the virtual world. So we need to set that to a sphere shape, and you can see that we've got a nicely fitting shape here. But I'm actually going to go and enlarge this shape a little bit. And we don't do that with a scale. This is one important thing to keep in mind. If you use scale to set the shape, the physics engine does seem to have some problems with that, or so I have been told. But you just splash on that little arrow thingy, so that we edit the shape properties itself, and we simply increase the radius size to 2, and that allows us to keep the sphere is relatively small in our world, so it doesn't become this huge thing that hovers above the world. But we don't need to be super precise in looking exactly at this tiny little dot or little globe somewhere off in the distance. We have a little bit more leeway to what we're looking at. Now, the last thing that we're going to do is add in a script here so that we can start automating some things. Navpoint.gd. Great. And in there we can put the logic for our static body. So the first thing that we're going to do here is simply react on the user looking at this sphere. We're not going to do much more than that. And for that we need to create a few variables and some logic. And the variable that we're going to create is called isHitting, which we will make true when the user is actually looking at the sphere, and the isHitting comes from our ray is hitting the object. We need a function that we are going to call from our raycast logic called setColliding. And again, variable needs a name. We're going to just copy that so we know what's going on. And we're going to react on that. Oops. And I'm just putting these passes in just as placeholders. We'll change those in a second. Because before I'm ready to do that, I need another variable, which is called mesh material. And the reason for this is I could set a material on my mesh in the material override or in the material itself. Am I using the override? Yeah, I'm using the override in this case to change this material. But I found out that when I use this navigation point scene multiple times in my scene, they would actually all be linked to the same material instance that gets created. And when I changed properties to highlight the navigation point that you're looking at, it actually changed all the navigation points, and that's something we don't want. So we're actually going to create a material on the fly so that each of these entities, each instance of this scene has its own material that we change, which is very simply a matter of creating a new fixed material. We're then going to set our color on this material. And it's enough for now to set our diffuse color. And we are setting that to a slightly transparent white. And then we are assigning this to our mesh. Oops. There we go. So that sets up our material, and the last thing that we're going to do for now is change our set colliding code so that if we're not hitting our object, we're setting it back to white. And for now, when we are hitting it, we are going to set this to blue. I'm going to do a little bit more with that later on, but that's just something that we want to start with. Yep, let's save our scene, make sure that we have it. All right, that's it as far as our nav point logic is concerned. So let's go back to our main scene and start adding our nav points into the world. But the first thing that I'm going to do is create a new spatial node, which I'm going to call nav points. And that simply allows me to group our navigation points together, and you'll see why that's handy in a few minutes. So I add my first nav point in, which will go and position. There we go. I just want to first make sure that is a little bit higher. I'm not quite sure why it's so unbelievably bright. Let's turn that off. There we go. That's probably why. So at this point in time, I don't really care too much where I put it. You can always fine-tune that a little bit more later on. So let's just do that one something like this. Let's go get a top view, and then we just place 4 of them around our scene. Oops. So we call this one nav point 1, and then we duplicate it so that we have another one that we can move. We put that somewhere over there. Duplicate another one. We'll put that one over there. And then for now, the 4th one. And we put it over here. Okay. So we have our 4 nav points, and now we need to add our raycaster. So I'm going to select my stereo camera view, or node I mean, and I'm going to add in a raycast object. And this is an object that is now linked to our stereo camera position, so it's nice and center, and it allows us to cast a ray into the world, which will automatically be evaluated by the physics engine, and when that ray hits things, we will get some feedback on that. Now, important to know, if you look at the original implementation of the CamBase and camera here in in our NavMesh logic, you would see that the camera automatically already has support for casting a ray from the center of the camera. And it uses that for when the user clicks somewhere on the screen to cast a ray from that location on the screen into the virtual world. Now, we're not using that for two reasons. The first is we've got two cameras. We've got a left eye and we've got a right eye, and they're both slightly off center. While for our logic, in our case, we are just interested in the direction in which we're looking, and doing that from the point nicely in the center between the two eyes makes far more sense than doing it from one of the two eyes individually. The second reason is that we don't have a mouse pointer that we need to worry about. We are always casting a ray from that center out into the world. And this makes life easier just by having that little ray casting there. The most important, or actually the two important properties that we need to set right now is, first of all, enabling our raycast. As long as that is off, the physics engine will ignore our ray and will not evaluate it. And the second property is the cast to, which is the direction into which we are casting our ray and the distance to which we check our ray. So we're looking into the screen, which is a -z value, and we're going to be looking 100 units away, which is pretty much beyond, very far beyond our scene. But for a small little world like this, you know, we don't need to be conservative with this. The other thing which is interesting to keep in mind, even though we're not really interested in it, is this type mask, which will tell the physics engine which entities we are going to check whether the ray hits it. So in this case, we could suffice with by just having the static turned on, but I'm just going to leave that default. The next thing that we need to do is to add a script to this raycast node. And again, I could put everything in our navmesh.gd script, but for these sort of things, I kind of like compartmentalizing it, which is one of the really beautiful things of that Godot allows you to do. So we are going to attach a script here, and I am going to call that I don't know, ray.gd. Oops, that was the wrong button. Attach scripts, ray.gd. I wonder if that was trying to tell me something, but if so, it didn't work. And in this little script, we are going to put the logic for reacting to what our ray is going to be doing for us. We're going to start with introducing one variable, which is called current collider, which will keep a reference to the nav point that we're currently looking at, if any, so that we can detect that we're already looking at the nav point, and we can detect when our gaze moves off of a nav point. And we are going to add in a function called fixed process delta. And for that, we also need to turn fixed process on. And this is very important. So far, we have been using the function called process, and we have turned on set process to make sure that that function is called every frame that we render. Fixed process is slightly different. Fixed process is synchronized with our the thread that is running the physics engine. The physics engine is actually running in its own thread. It is parallel to the main thread, which is doing all the rendering. And if you will be handling stuff in your main process, there's a good chance that you will be working against logic that the physics engine is still busy processing. By handling our logic in the fixed process method, we are ensured that our physics engine has processed everything, is in a state that it's ready for us to react on everything, and well, you know, make safer code, I guess. So while we know that this is going to be enabled, we are going to check for our raycast to be enabled. Remember, we've got our script on our raycast itself, so everything that we are writing here is in relation to our raycast. So we check whether the raycast is enabled, and then we check if our ray is colliding with something. If it's colliding with something, we need to react on that. If it's not colliding on something, and that's the first thing that I'm quickly going to put in there, I'm going to check if I was colliding with something. And in that case, I need to tell that collider that we are no longer looking at it. So let's start with that bit, because that's nice and quick, by calling that setColliding function. And we're happy. Now, in our little example, obviously we know that the only things that we will be colliding with are our nav points, because that's the only object that has a static body associated with it. But obviously, if you've got a more complex environment, you probably need to do a little bit more here to make sure that you are detecting what am I actually looking at. Am I looking at a nav point? In that case, I need to call the property setColliding and set it either to true or false. But if I'm looking at one of the other objects in my scene, I might need to react in another way. Just quickly sidetracking on that subject. One thing that is really nice is if we would be using this raycast solely for the nav points, and we will be using other static bodies and or rigid bodies or any other physics objects for other reasons, we would be able to set different layer masks to ensure that this raycast only interacts with other objects that are in the same layer, and we could put this raycast and all the nav points in the same layer and put other objects into different layers, and in that way segregate things, which is one of the nice features in Godot, to separate things out without having to write a whole bunch of code to make sure that you're calling things in the right order, or you're calling things that actually exist. Okay, let's do the more difficult one, the actual isColliding function. Well, more difficult, a little bit. We're first going to get what we are colliding with according to our physics engine. Our physics engine will have set this property on our raycast if we're colliding with something. Excuse me for the motorbike that just went by. And now we're going to see if we were colliding with something before. We want to see if we're still colliding. Well, let's be consistent with how we name these things. We're going to test if we are still colliding with the same object. So we already started looking at nav point 1. We are still looking at nav point 1, and that means, don't do that. There we go. That means we don't actually have to do anything anymore. Oh, that was one tab too many. But if we are going to be looking at a different object and we do have a current collider, obviously we first need to tell that collider we are no longer looking at it. Let's make sure we have the right number of tabs. So if we don't have a collider, that bit will be, or we had a collider, that bit will be skipped. If we do have a collider, we're checking whether we're still colliding with the same object and not doing anything anymore. Or if we are now colliding with a different object, we are telling our old object we're no longer colliding with you. And finally, we are going to tell our new collider we are colliding with it. So we are going to tell our new nav point we are now looking at you. So we're going to first remember that we are now looking at that guy, and that now means that I can call setColliding to true. All right, let's see if that works. Okay, as we can see, there's our platform. There we've got one of our nav points. There's another one. Oh, we can already see that our ray is working. We are looking at our globe. Every time we look at it, it becomes blue. And as you can see, it has a bit of a range. So we can look at the other one. There we go, goes blue. There's one that's nice and close to us. And there's probably one, yeah, over there. All right, so far, so good. Okay, we're back in our navpoint.gd file. Because obviously it's nice of this globe to change its color, but we need to start making this do a little bit more. What we're going to be doing is the raycast is responsible for looking at a globe and telling that globe, I'm now looking at you. Tell that nav point, I'm now looking at you. But it is then the nav point that will handle, okay, I'm being looked at and I'm now being looked at for more than a second or two. And I am going to let the rest of the application know, okay, user has looked at me long enough, go and react on that. And we're going to use signaling for that. So, extend static body, we're going to first define a new signal which is called nav point selected. So when this nav point deems that the user has looked at it for long enough, and we are now going to select this nav point as our new location, it is going to send out a signal, and well, we'll have something react to that eventually. We also need a counter so that we can slowly figure out how long the user has been looking at this thing, and we need to now extend our set colliding function to start our timing. Now, one of the things that I'm going to do as part of that to give the user some more feedback of whether he's looking at something and whether the nav point will do something, instead of it just turning blue and then the user going like, okay, nothing's happened, it's turned blue. Let's make it slowly turn blue, and when it's then fully turned blue, that is the moment when we actually move to that location. So our logic here is going to change slightly. I'm going to disable that for a second, and I'm simply going to set our value to 0. I start counting at 0, and I'm going to set my process to true. So from that moment onwards, I'm going to start calling my process method. Now, keep in mind that in our nav point, in our ray.gd script, we used fixed process because of the way that the ray was interacting with the physics engine, and the physics engine is running in a separate thread. This function is still called within that set fixed process flow, but obviously by the time we turn this on, our complete handling of this can be outside of that. We can just do that the normal way. When we get our set colliding set to false, so the person has looked away before our second or two has passed, all that we're going to do is turn set process off, and that will stop our process function being called every frame, which means that none of the rest of the logic is going to run. So nothing will happen, well, except for our globe turning back to white. So what about our process function itself? So in here, we are first going to extend our value by delta. Delta is the variable sent to process, which tells us how many seconds have passed since the last frame, which will be something like 0.000 something, because obviously we are getting called numerous times a second. So that value very slowly creep towards 1. And we're going to say that once our value reaches 1 or gets bigger than 1, so once 1 second has passed, I'm just going to set the value to 1, and that is just because I want to set the final color on this thing. I am going to turn my process off, and I am going to admit my signal which is going to tell something else in our application that we have now looked at this nav point long enough. And I'm also going to send a pointer as a parameter to whatever is subscribed to our nav point signal, so that it can evaluate, hey, which nav point? Well, nav point 3 has just told me that it has been selected. But we're not doing anything else. Obviously, there's a whole process that now kicks off, which will reposition our camera and hide the nav point that we're at, and all that sort of thing. But that's going to be handled outside of this function. All that we are left to do in this function, if my mouse wants to work, is change the color. That's why I kept that around. And we're simply going to say, for our red and green channels, that we slowly move from 1 to 0, because we start at 1, take off 0, because that will be the value at the start. The value will slowly increase until the value hits 1, and at the end 1 minus 1 is 0, and we are at blue. It's that simple. Okay, so let's test this intermediate stage. Obviously we won't actually get to the nav point, it will just slowly turn blue, and then that's all that's going to happen. Okay, so we're back in our virtual reality application. There's our white little globe. Let's look at it, and there we go. Now instead of turning blue right away, it turns blue slowly. Once we look away, it obviously goes back to white to indicate to the user that they canceled the action. So as long as they move away in time, we cancel. Alright, now let's actually move to our nav point. Okay, we are now in our main navmatch.gd script, and that is where we are going to do the next number of changes. But first we're going to do a little bit of housekeeping to make our life a lot easier. And the first is to create a new camera variable, which we're going to set to our camera. We are going to add a variable for orientation, and we are going to add a variable for the current nav point that we are looking from. Now, right now, none of these nav points are current. Our camera location is wherever we started at, but that's actually one of the things that we are going to change in a minute. So let's go and replace a few of these. So let's start with the camera. Oops, camera. Let's see where we're using that as well. That code we'll get to in a minute. So we want the camera over here. We obviously want to set. Oops, that didn't help. Let's do that again. My apologies. I was thinking I was copying something else. So we got to go back up here. No, I did do it right over there. So yeah, I think those are good. And the other one was orientation, which is going to become our root orientation. And it saves us a whole bunch of typing. It saves Godot having to look up those nodes all the time. So it's just something to make everything slightly faster and slightly more elegant. There we go. The other thing that I want to change, let me have a good look. When we're looking at our process, I'm pretty happy with that. That's working pretty nice. Our update path pretty much stays the way that it is as well. You can turn that draw path off if you want. There's a variable upstairs you can set to true, and it will actually show you the path that little robot is going to take. I'm going to leave my input event here for now, but we're going to be changing that very soon. But I am going to remove this thing, which is the mouse logic to change our camera position. And for people who have been trying out the The previous versions of this, who've been getting the source code from my GitHub page, probably have run into, even though the application runs, it will have been complaining about this input event, that it's actually calling a whole bunch of things that are turned off and not working because you're not on a normal desktop. We leave our process input intact. We leave that intact. So yeah, that is our little bit of housekeeping done for right now. All right. Let me just get to... Yes. We first of all need a new function, which is going to be called onNavPoint selected. And that is going to be the function that will be called by our signals that we defined in our NavPoint GD script, and that will actually handle changing the location of our camera. So the first thing that it's going to check is, have we currently got a existing nav point selected? And this will always be true except the very first time we will be calling this function. And it's very similar to what we did before, where we first check, is this the nav point that we've already got selected? Should never happen, but in that case we just get out of there. But if it is a new nav point, we are going to show this nav point. Now, that seems strange because we never hidden any of these nav points, but that is actually something that we're going to do in a minute. Whenever we select a nav point, we will be at the location of that nav point. We will be inside of the physics shape of the nav point. So our array will immediately hit our current nav point, and we don't want that. Plus that, depending on whether you are using a double-sided material, we might end up only seeing the inside of our sphere, which is also not really what we want. So when we have our new nav point, we are obviously going to remember our new nav point. And then we're going to hide our new nav point. There we go. And finally, we are going to move our camera into position. I could do this as a one-liner, but I kind of like splitting this apart, so if I'm debugging, I can actually see what's going on. And as a bonus, we are also going to update our base, our null orientation look-at orientation for our camera. And for that, we're actually going to copy, or actually move that bit of code into here, so that we're going to make sure that whenever we reposition our camera to the nav point that's now selected, we are going to make sure that the I am looking forward look at is going to again look at our scene. Because remember, we are at one side of our scene, we're looking at a nav point at the other side of our scene. We go there. If we keep looking in the same direction, we will have our platform to the back of us, and we will force our user to turn around. While if we turn around for him, he at least orientates himself to the camera. Sorry, to the platform. However, one of the things that we also need to do is to request a new reference frame. Because we have now told the system to make the new looking direction forward, but of course we have to undo the current rotation so that we don't actually end up still looking into the wrong direction. And we simply do that by requesting a reference frame. Okay, Now, seeing that we have removed our code over here, and I didn't do that by accident, we now actually have to reinitialize everything here by, going to the very first nav point. So we are just going to initialize by going to nav point 1. Let's go to the first one. There we go. Okay. So if I would start my application right now, or my game right now, the very first thing that would happen is that we're going to select nav point 1. There isn't a current nav point, so we're going to skip that bit. We're going to assign it. We're going to hide nav point 1. We're going to move the camera to the location of nav point 1. We're then going to look at the center of the screen, and we're going to request a new reference frame, which would have been requested anyway, so that first time that will not do anything. There's still one ingredient missing, and that is that when I'm looking at my nav point, or one of the other nav points in this case, and I look at it for long enough and I get my signal, nothing is listening to my signals. And that is why I placed all the nav points into a container spatial. Because that allows us to do something very simple to get all our signals hooked up. We're going to loop through all the children of our nav points node. And we're going to tell each one of those that we want to react on our nav point selected signal. We want that to be sent to ourselves, which is our main script, and we want to call our on nav point selected method, which is our method up here. So this is a simple loop that gets called when Godot starts. It will tell each and every one of those nav points that I want to react onto the nav point selected signal, and it should, whenever that signal happens, whenever it emits that signal, it needs to go on and call our on nav point selected method, and that will reposition our camera. Let's see if it all works. Okay, I made one small mistake. We'll get to that in a second. But as you can see, we are now at a different location in our scene when we start a little NavMesh demo. And well, let's see if we can find a globe to go to. Boom. So we were looking at that one globe, and voila, we are now looking towards our scene from another direction. So let's see if we can maneuver around some more. Ooh. Now that is a bit of a surprise. We are now actually looking exactly at one nav point. That's what you get when you nicely put them in a plus orientation. So hey, that's another mistake that we need to correct. We need to move the nav points slightly off center from each other, or we end up rotating like this. That was fun. Okay, we're back in Godot, and I went to the navpoint.gd script. The only mistake that I had made was a typo in our navpoint selected signal that we are emitting here. I had nicely called it navpoint selected at the top. I had called it navpoint selected in our other script, but here I had called it navpoint selection, and of course it doesn't like that. Two things that we need to change. The first one, we go back into our little scene, and we're going to move our nav points around slightly, because as we saw, we were looking from that to that. That went all right, because we sort of ended up in a different place, and because I was looking to the left, after I moved to this, I was still looking a little bit off center. But once I went to this one and I looked at that point, I wasn't looking at that, I'm not quite sure, but I kept flipping around and it kept looking exactly at the next nav point. Then next time we started rotating around the nav points. So in theory, by just moving our nav points around just a little bit, oh, I got that one selected, that's why I didn't see them, and making sure they are slightly off-centered from each other, we in theory should prevent that from happening again. There we go. Perfect. I want to create one more nav point. Where are you? Duplicate. We're going to call that nav point 5. And I'm going to move that somewhat to here. I don't want it exactly in the center because our look at is looking at the center, and we'll have the logic there panic a little bit when we do that. But I want to have this one all the way up. So we have got this little point that we can look down at our platform, and we can send our little robot up. As we're busy with cleaning up anyway, let's get rid of our old camera over here, which we no longer need. There we go. That is completely being replaced now. And then there's one more thing left to do, and that is to actually control our little robot. So for that, we're going to look at our input function. Here we go. We already removed the logic for rotating around the camera, as that is no longer applicable. But we now want to change our logic here to logic that works with our stereo camera. Now, most of the cardboard style VR HMDs, and as far as I'm aware, the same goes for something like a Gear VR or most of those sort of things. They have a little, they either have the little magnet on the side, which we are not reacting to right now, but we could put some logic here to see if there is a big change in the magnetometer. And if there's a big change in the magnetometer, we know that someone's moved a little switch, and we could react on that. But most of the newer headsets that are coming out are no longer taking that route, so I'm ignoring that for now. But most of the other ones, they usually have a little lever that you can press through a button on the outside of the headset, and that actually pushes something against the screen, which mimics a touch event. When you look at something like a Gear VR or things like that, I believe that that is part of the headset itself that actually sends a signal that gets mimicked as a press on the screen. But under that assumption, I don't have a Gear VR, I haven't been able to test it, but under that assumption, that's the way that we are going to react to this, as many of the cardboard type headsets work that way anyway. And it demos our approach pretty well, and it gives us a good starting point to implement other things. So that means that we can actually keep most of this logic alive when a user touches the screen on a phone. Godot processes that like a mouse click, and we can therefore react in the same way, but we have to obviously change our code here. Now in this case, we're not going to use the Project Ray Origin and Project Ray Normal because we don't actually have access to those properties. We have access to the properties on our Raycast object. So instead, actually we're not even going to use that. Sorry, I'm going completely in the wrong direction. We're simply going to use our location information from our camera. Get node, camera Raycast. I could use the camera node itself directly, I guess, but yeah, this works good enough. This is what I did in experimenting this, so I'm not going to break that. So I'm getting our transform, but I'm getting our global transform. I want to make absolutely sure I am getting the global location and orientation of our Raycast. Then our from becomes really, really easy because we simply get our origin point of our current camera, and then our to becomes that origin point. But we are going to take our bases and we're going to X-form that, and we are going to take, well, we could obviously take our Raycast vector, but works just fine to hard code that. But we are going to apply our vector rotated by the rotation matrix of our camera, and and that gives us a nice pointer outwards of what we're looking at. And the rest we can keep the same because the logic works exactly the same. Our pathfinding logic uses that vector from our camera location to our look at location as the vector to use. And it does the same pathfinding that it did before. It actually doesn't change anything more than that. However, I'm going to do one more thing, because when I did this first time I found out that it worked perfectly, but it was really hard to see what we are actually looking at and where we are trying to make our robot go. So I'm going to abuse our little sphere mesh again. There we go. And I'm going to make that really, really small. Well, pretty small. There we go. And I am going to put that a little bit into the world. I'm not quite sure if that's going to be enough. I might move it a little bit further. Well, actually, let's move it a tiny bit further. And that gives us something to look at. This is basically just going to hover sort of like a few, a few centimeters in front of us, and it works like a bit like a target reticle. Now it would be really nice if I could actually make that be set to the distance of where I'm hitting the platform, and that is something that I might look into, whether I can get that information, whether I can get that intersection point from the pathfind logic, because obviously it will have calculated that somewhere, but I haven't looked into that far enough yet, so that we can actually see on the platform what we're looking at. But for now, this does enough to give a convincing reticle to give you an idea of, that's what I'm looking towards. That's what that's a part of the platform that I will be sending the robot to. Let's see if that all works. Okay, here we are. I still think that little aiming ball is slightly bigger than I would like, so I'll make it somewhat more smaller in the final version that I'm going to check into my GitHub page. But you can see that that it gives us a little bit of an idea what we're aiming at. And when I then click, there we go. Our little robot moves to whatever location I am looking at. Now let's go to that little globe that we moved all the way at the top. Again, the shocking movements that we are seeing. I have to say this is easier to do when you've got the headset on. The shocking movement of our of the video here is mostly the streaming that is not up to par. It's actually really smooth on the iPhone display itself. But yes, we can see it move around quite nicely. Go, robot, go! Alright, let's move it to a little bit more comfortable location. Where are all my location balls? There we go. So, go, robot, go. Alright. Hey, it works! We have a completely working VR implementation of our little NavMesh demo. Now, obviously, that aiming reticle would be, using a sphere for that is quite a bit of a cheat. It would be nicer to have a more proper stand-in for that. The same thing for these globes that you navigate to. There's probably a nicer object that we could use to make that more friendly for the user. I do have to say this. Looking at it as a screencast like this doesn't really do it justice. It's a lot more fun to see this actually working on a headset. It really gives you quite a nice sensation, and I gave this to my kids. They really loved it. They had quite a bit of fun to it until they figured out that all they could do was move the robot around and they couldn't score any points or anything like that. But that's the proof of concept basically that we've done, and this gives us a nice skeleton architecture to do a very simple VR game in Godot. There's quite a bit of room for improvement. I already mentioned, obviously not using globes for navigation and a reticle like this. But the orientation code can probably be polished up a little bit more. I found out that after I ran from one end to the room to the other to give this to my son, there was so much vibration in the accelerometer that the screen started shaking a little bit, which was really annoying. So it definitely can use some better filtering on the accelerometer. The gyroscope is pretty rock solid, so I'm very happy with the gyroscope logic. Obviously, there's room for improvement looking into the magnetometer and putting that in. And the setup, you know, we haven't really handled the setup of this at all. We've just hard-coded some of the values in here that are right for my phone and the HMD that I'm testing with. But it would be really nice to have, you know, a setting screen in here that allows you to select what HMD you have and get some basic parameters and stuff like that. But you know that kind of goes beyond the scope of this little tutorial series. That might be something that we start looking at in some sort of follow-up series. Another thing that I really would like to look at some point in time is some alternatives to the lens distortion. So instead of using rendering to a much larger resolution bitmap, or render texture to actually distort the objects that we render, and do everything in much more effectively with much less overhead. But yeah, you know, it's a great start, this one. I hope you guys enjoyed this little series. And yeah, give me a like and subscribe to my channel. There's more to follow. All right, see you next time.